It's a great pleasure to introduce our speaker today, Abigail Polin. Abby did her PhD in Berkeley and then moved to Carnegie Observatory and Caltech for a postdoc. Recently, she just also moved to Purdue University as an assistant professor. So Abby is an expert in simulation of transient phenomena. And today she will tell us about her beautiful work on supernova remnants.
Thank you very much. Yes, so as you just mentioned, I'm currently transitioning to Purdue University as an assistant professor. I'm technically there, but technically haven't started, so it's the best of both worlds. So most of the time, my science involves transient theory. And what I'm very passionate about is developing methods of being able to directly compare theory to observations, directly test our theoretical ideas with real supernova observations. In the past, this has mostly been in the form of thermonuclear supernovae explosions and radiative transport modeling to be able to compare our different progenitor channels for things like type 1a supernovae and calcium-rich transients to the observed data. I'm one of the developers of Sedona, radiative transport code, which is what I use to do those things most of the time. But today I'm going to be talking about something new that has very much developed from talking with other professors at Purdue University. Before I start though, I'd like to point out we are hosting a transient conference at Purdue this summer. Registration closes in a week, but registration is free. So it should be very good. We have a great lineup of invited speakers, and we would love to see some of you there. Registration closes the 26th though, so I wanted to make sure I said this and said this clearly and posted this here. Right, so let's talk about supernova remnants. I've been talking about supernova remnants a lot since starting to spend some time at Purdue. Specifically, I hear a lot about CASE. And maybe you have heard a lot about CASE recently too, because it turns out what I think is going to happen, what a lot of other supernova people think are going to happen, is JWST is going to kind of revitalize the field of supernova remnants. Supernova remnant physics is hard. There's not that many nearby ones. Spectra are expensive, but being able to look at them in a new lens will reveal new information. So this is CASE and Hubble. CASE is a core collapse supernova, very nearby. We can kind of see the outer edge, some information here. Obviously, we learn a lot more if we can look at this in the X-ray. And this is where most of our data of imaging, anyways, of supernova remnants exists, these X-ray images. And you can see a lot more information about what's going on in the shock region of the supernova. But JWST allows us kind of to see past that into the unshocked regions. What's going on, not just where the supernova is interacting with its circumstellar medium, but what's going on under that. And this should really be able to help us, in my opinion, learn something about the supernova if we can see through the surrounding stuff, right? So this is one of the first JWST programs on remnants, led by fellow Purdue professor Rayleigh. And what I'm going to talk about today kind of arose from many a journal club of Nan and I just kind of back and forthing, pointing at things, going, I bet this is this. And I said, okay, but how do we know? Show me what that tells us about the supernova. So the question I had was, what can we tell? You know, I'm fundamentally a fluid dynamicist, first and foremost. And when we look at supernova remnants, there's wildly different structure. Obviously, this is related to the wildly different physics involved in these different types of explosions. But the question I wanted to ask was, what can we tell fundamentally just from the structure of the remnant itself about the supernova that went off, right? What can we learn with this most prevalent type of data, these X-ray images and more images, but what can we learn about supernova physics from images of supernova remnants, right? Because we have spectra, but spectra are hard. And the idea that eventually arose, how do we compare these two, right? So this is a simulation of a supernova remnant. This is Tycho. They kind of look first principles the same, but how do we actually compare them back and forth, right? If you take any explosion and expand it for 1,000 years on a theory perspective, it'll kind of look like a remnant, right? That's how physics works. I want to be able to make direct comparisons. And so the idea arose, and you might be able to guess what it is by either reading my abstract or taking a look at this is the same simulation, but in a more wide projection. So does anybody understand where I'm going? Right. I wanted to ask the question of what if we took our supernova remnants and did the same things you do to the CMB, convolve them into angular power spectra, right? This was a really powerful idea when we did it with the CMB, but why it worked was because we had spent years trying to understand the physics that drove the CMB. We came up with templates, we had expectations, right? And so when we imaged the CMB and we took our power spectra and saw those peaks, we could directly say, well, yes, this peak aligns with what we thought this physics was, this physics, and this physics, right? We don't have that for supernova.
But it only works for spherical, quasi-spherical things, right?
Remnants are quasi-spherical.
Well, with the crab, we don't have anything.
Crab's a little harder, right? Crab's a little harder, right? The more asymmetric physics you get, the harder it becomes. But crab still has, you know, these wildly different angular scales. They have the, you know, the tiny turbulence, the big holes. I grant you this will be a much harder problem than something like this, right? But even this would be wildly powerful to have a template expectation of what a type 1a supernova driving physics would predict here, right? So this was the basic idea. What can we learn about supernova remnants through power spectral analysis? And very similar things have been done before, it turns out, once, you know, I stopped just thinking by myself and go through literature. But a lot of times what we do is not angular power spectra, is we take a picture of a supernova remnant and we do a Fourier transform. And when you do that, you just get that remnants are mostly spherical, right? So our goal here, the first paper I'm going to talk about was just saying, okay, is there anything to this? Is a power spectrum of a supernova remnant interesting, and what physics drives it? And in order to do this, we started with the simplest example of something remnant-like we could come up with, right? So please feel free to interrupt me during this talk. I love interactive talks, but I know this is not a supernova remnant, so don't jump down my throat in this. So we wanted to start with the simplest thing because we, you know, understand the parameters that go into it. And what we did, we chose a Chevalier self-similar solution, right? You just have one power law of supernova ejecta running into a different power law of CSM, right? And this advantage of this kind of situation is it evolves to be self-similar, right? So we don't have a time variable. There's no time scale in this problem. So this is what it looks like when you do this. These are simulations of Chevalier self-similar solutions using the JET moving mesh hydrocode. So JET is great for this type of problem because it is a moving mesh code derived in kind of angular bins. So that cells grow and shrink in a radial direction, but not the cells themselves don't shift along theta. But it allows you to run something like a remnant for very long dynamic times without losing information to numerical diffusion. So fundamentally what we're looking at here, up here, we'll have a forward shock. Down here, we'll have a reverse shock. In between, you get a contact discontinuity that becomes Rayleigh-Taylor unstable, right? This Rayleigh-Taylor instability, in this case, is self-similar, right? So it grows along the same scales constantly once we reach a turbulent state. And so the first thing we wanted to say is, okay, what is the power spectrum of this, of a self-similar Rayleigh-Taylor instability? Because this is a fundamental process that we should see in all remnants, right? All remnants are fundamentally something running into something else. And, right, I can skip over the math of remnants.
This is a constant velocity propagating.
This is, yeah. Into a static mean. But But right, fundamentally, power spectra are just something you can do. Any smooth function can be represented by a sum of spherical harmonics. You invert it, get the power. And when you do that for these Chevalier self-similar solutions, this is the power spectrum you get. The different purples here are just my different resolutions of simulation to show you that this slope is real and this last peak is just my grid scale. How you should think about this, so this is power. This is L. L is inversely related to theta. So higher L's, smaller scales, turbulence is over here, supernova physics is over here, right?
It seems there's a peak at around 10. Is that related to the periodic boundary conditions?
I will get to that. That is the most interesting piece of this power spectrum, right? The fact that it clearly has a peak. But before we get to what that peak is, because that was a big result, let's break this up a little bit.
Sorry, what is this power spectrum of? I mean,
This is a power spectrum of radial added density along radially added density, and it is pressure weighted, so it's just the shock.
Oh, it's radially integrated.
Yeah. Yep. So that will become maybe a problem later.
Yeah, I mean, can you do it on slices and radius? Kind of cuts and radius.
We'll get to that,
Okay.
yes. Yeah, so this is almost like cuts in radius because we pressure weighted it, so it is only the turbulent region that is.
Okay.
Right. So fundamentally, this is our power spectrum of Rayleigh-Taylor turbulence of the self-similar Chevalier solution. Over here, we have our turbulent region. We have a very, very steep slope, and these are 2D simulations. So maybe it's okay, but maybe it should very much concern you that this is not a Kolmogorov scaling here. We're not seeing Kolmogorov turbulence. Even a 2D Kolmogorov, when you conserve your vorticity, should have a scaling of L to the -3 here, right? So this was unexpected and uncomfortable, right? But it's 2D simulations for now. Maybe it's fine. Maybe instead of Kolmogorov, it's a self-similar solution. There's only one length scale. Maybe we're seeing just the growth rate of the Rayleigh-Taylor instability in an expanding medium. Maybe we do never reach a turbulent cascade. Over here, there's a very steep slope that in itself is not so important. These are perfectly spherical explosions, but the fact that there's such low power here is good because one, spherical, two, this is where we should look for signatures from the supernova itself, right? If instead of a spherical explosion, I had something with jets, I had something that was a core collapse supernova with nickel bullets, right? That's where this would imprint angular scales that we should start to diagnose. So it's very good that this is low power, right? Because this is where we will look for physics endemic to supernovae. Because the peak here represents the smallest scale that you can see supernova physics, or the largest scale dominated by turbulence, right? Yeah.
Really dumb question.
Yeah.
You have a dashed line with slope L cubed,
Yes.
but your actual data looks a lot shallower.
Yeah. This slope here is unimportant, right? So yes, I agree. It's hard to get an actual slope there. This slope was gotten from a huge parameter space of simulations instead of just this one. But I was not all that careful because there's nothing there, and in real life there will be something there, right? But yes, I agree. In this case, it does look like it should be a little shallower. So, as you already pointed out, the very interesting thing here is this peak, this dominant angular mode in the supernova remnant. And our question in this paper was, okay, now that we've shown this is kind of the characteristic simplest power spectrum and the simplest remnant model we can come up with, what drives this peak, right? What causes this peak here? What causes the dominant angular mode in the supernova? And when you think of the image of Tycho I showed earlier, like there obviously is a dominant angular mode, right? It's got this cauliflower surface. You can see by eye something should pop out. It would be great to know what physics is responsible for it. So in order to start to suss that out, to figure that out, you have to run a parameter space of models, right? You can't just run one. You're not going to learn anything from one, which is why we started in 2D. because computationally 2D is much less expensive. We can start there and say, can we learn anything? So I ran a very large suite of models with varying density power laws of our supernova and density power laws of our CSM. And here's the results, and it's super messy, right? So these different colors here are different supernova ejecta power laws. And over here, sorry, it's covered by the data because I just added this plot to the top. This is a constant density CSM. This is wind-like CSM. It's a mess. This peak is located, it spreads, it's hard to find. But what we realized we could do is instead of plotting power versus L, we can do power versus L over N, right? And then something very interesting arises.
What is it?
N is the power law of the ejecta density. So when we do that, we get the same function, this best fit line in green. All the peaks line up. They line up at around L of 3, L over N of, no. Yes, L over N of 3. Yeah, I can count. And the same happens in both the constant density CSM and the wind, right? We get the same peak here. It is very cool, but a little uncomfortable. Because what this is telling us is that this dominant angular mode does not care what medium it's running into, which is really good for a supernova physicist because it means it only cares about the details of the supernova, right? So, yeah.
So if it runs into an inhomogeneous medium, you have other instabilities like,
I'll get there.
yeah, that's why this.
I'll get there. So first of all, these are uniform mediums right now. So that's a very good question. And we did test to see if that would matter, and I can get there in a second. But more fundamentally, the answer was no. It doesn't. It washes off those. It just stirs turbulence more quickly. But
So in the when you do 2D simulation, to simulate all the angles, or you
Yes.
have some?
yeah, this is full. It might be a hemisphere. Now that I think about it, I think it's a hemisphere.
Okay, but not smaller.
And what physics do you put in? Is there any cooling?
There's no cooling yet. Yeah.
Diabatic.
Yes. Yeah, it's just a gamma.
The density just jumps to 4 and stays at this level behind the shock.
Well, the density jumps to a dominant angular mode of,
No, I mean,
Oh.
as the fluid crosses the shock, it just.
yes, yep, if you just get it's just the purest Chevalier. So
So it was, sorry, it was uniform, but did you add small perturbations to
we
see?
do later.
Sorry?
We do later, yes, but not in
just
this.
here to-
No.
So what seeds?
Oh, yes, we add, sorry, yes, we add the smallest numerical tiny, yes, to seed Rayleigh
What's
Taylor
the power spectrum of
power spectrum
that?
of.
Of this perturbations that you're putting in, is it just white noise?
Yes, it's just white noise to start with. We then, I'll get to see purposefully periodic and chaotic clumps that then stir the turbulence themselves, but yes. So empirically, we find our dominant angular mode, or dominant L naught, we call it, is proportional about 3n. Again, n is the power law density, power law of the supernova density. And what this relates to is just the scale height of the density scale height of the ejecta. So this is very cool. And when I should put up the picture, this makes it easier. So what we're looking at here is, here's a number of different simulations of different supernova ejecta running into, again, static wind. And what we end up looking at is this dominant angular mode is unsurprisingly dominated by the width of the largest Rayleigh Taylor finger, which only cares about the density structure of the ejecta. So this could be very cool because, again, this is something we can pull out of 1A remnants, right? There's obviously a dominant scale in these cauliflowers. You know, we'll take some tricks to figure out how to measure it, but you can see by eye, there is something there. And that should relate, again, to this largest finger. And there's more physics we include later, don't worry. But this is cool for us 1A scientists because we have so many different ideas of what a type 1a supernova could be. And their outermost ejecta all have very different steepnesses of their slopes. So ideally, hopefully in the future, what we can say is, oh, well, this dominant scale tells us that the region that is, the forward shock is going through, or the reverse shock is going through rather, relates to a specific steepness and density, and that can help us start distinguish models, especially for these remnants where we know their age, right? We don't have to just work with dynamic age. We know their actual age. So this is very cool.
Do you expect the structure size also to change as the ejecta?
In real life, yes. In these self-similar solutions, no. That, they're self-similar. That's the idea of them. In real life, we don't expect a supernova to be a Chevalier solution. We expect it to have something more like a exponential density profile, and then that has a time component to it. So
Okay,
yes.
and in that case, the end will be the local
Yes,
state.
yes, exactly. And we do that later. But to get to your question, what about clumps? Because again, this is very uncomfortable, right? If it does not care what it's running into, how much does it not care about what it's running into? And yeah, it really didn't care about clumps. So these we seeded now, I didn't put but we seeded basically sinusoidal clumps. And it did not care about how many clumps we added or what density until the density of these clumps became comparable with the supernova ejected densities themselves. So very strong clumping, it will care about external clumps in the CSM. And something like a giant hemisphere running into a star forming region, it will definitely care about. But those are things we can see in other ways, right? So for tiny, invisible, inhomogeneous CSMs, all that does is seed our turbulence faster. But the forward shock just blows through it, and the power spectrum is not sensitive to that kind of clumping. So again, these are external clumps. This is our 2D paper that was just proof of concept, like maybe this is a cool idea, maybe this will be useful for somebody, maybe there's some physics we can get out of it. There's a lot of questions that are left. Why is that turbulence region not a Kolmogorov cascade? Do more realistic models behave the same way? They still have a dominant angular mode that tracks the density scale height. What about internal clumps, right? Because external clumps just seed our turbulence, but what about strong internal clumping or strong internal asymmetries? Do those show up? We hope they do, because that's the whole point, is being able to take these power spectrum and tell you something about the supernova. And most importantly, is this kind of calculation possible to perform on actual data, which is not a 3D sphere, it is a 2D projection, right? So the rest of this talk, the rest of the time I have left, I really want to highlight work not that I did, but that is coming out of my group from my graduate student, Sean Mandal. It says finishing here, but he's so happy in this photo because this was right when he passed his defense. So finished. He is going on to a postdoc at the University of Virginia, and he's phenomenal. So I'm a theorist. I try to be a theorist who cares about observations, who checks on observations and goes back and forth. But sometimes I still get stuck in theorist mode. So I put out this paper and said, okay, well, my code, Jet, that I was working with can't really do 3D, but maybe somebody will do it later. Like, this probably isn't possible to do on data. So I'll just put the idea out there. And he's like, no, I want to see a 3D. I want to keep going. So he's very eager. So he phenomenal. I guess I do have an animation. Sorry, I told you I didn't earlier. But he wrote a code in order to be able to do this problem in 3D, because Jet's not so great in 3D. So he wrote a code called Sprout. It is a 3D hydrodynamic code with an expanding mesh. So as time goes on, your mesh gets larger, and that's how he accounts for so many changes in scales that remnants have to go through from time of explosion to 1,000 years. I told him this was a bad idea. This was a bad use of graduate student time as a senior graduate student. I was wrong. He did this so quickly. He's a really, really phenomenal student, so keep your eye on him. But with this, he was able to revisit this problem. And I'm going to go through this quickly because this is mostly just to tell you, we don't have to trust 2D turbulence. We did check in 3D. So these are his 3D simulations of supernova remnants. We get the same power spectra. And most uncomfortably, you know, we still get a strong angular mode. He found a small shift between our predictions in 2D and 3D. I think he gets 4N instead of 3N. But more uncomfortably, this is still too steep to be a turbulent cascade. So I can no longer raise my hands and say, well, why would you ever trust 2D turbulence anyways? So we really think what we're looking at here, this slope, is the growth rate of the Rayleigh-Taylor turbulence in an expanding medium instead of a true turbulent cascade, which isn't terribly surprising because there's really only one scale in this problem, which is why we choose Chevalier self-solution solutions to start with. But it's uncomfortable.
Sorry, what is the normal power spectrum of Rayleigh-Taylor instability?
I mean, this is what we're doing. This is what we have to go with, right? So this is us saying, well, maybe it's this,
Okay.
right?
But is there a dimensional analysis kind of argument like for overall, which can predict this kind of power exponent?
We did not come up with one. I still think there should be, and we did not make it happen.
And the turbulence you see, this
Yes.
figures,
Yep.
doesn't look like an isotropic.
It does,
turbulence, so
no.
That must be one key difference.
Yes.
And you're not getting the.
Yes, I think so. And there's a lot that goes into this. Before I jump forward though, I will say Sham in his multi-D and 3D simulations did check on our external clumping and also internal clumping. And showed again, external clumping did not care until the density got absurd. And internal clumping, he's calling this A instead of delta, but internal clumping, strong internal clumping does show signatures in the power spectrum that hopefully can translate to comparing real data to things with nickel bullets, with jets, etc. So this is a future direction that I care very much about, doing this sort of analysis on more realistic, especially core collapse simulations that have asymmetries and, you know, expanding nickel jets, and jets themselves. I said nickel jets, I mean bullets versus jets, but trying to diagnose their power spectral signature and actually working backwards to be able to compare this region to the supernova physics. So Shom also then, because he's phenomenal and just keeps going, decided to take a look at the question you asked of what about a more realistic ejecta profile? So this, instead of a Chevalier self-similar, is an exponential ejecta profile, which is a lot more similar to all of our 1A explosion models. All of our explosion models typically have at least the inner part of the ejecta is exponential and maybe the tail deviates slightly. And this is his results that I showed earlier. This is our
What is
model.
new? Sorry.
Sorry?
What is new?
Sorry, this should not be a nu, that should be a v, velocity. Yes. And then there's a characteristic velocity there. Yeah. So again, this becomes time dependent. This is our density squared in order to kind of model an X-ray emission. And finally, when we look at the power spectra of this, we do see at first in the young phases of the remnant in blue here, we can let time goes from blue to red. We get that same alpha -3, too steep for Kolmogorov. But as the reverse shocks more and more and more of the supernova remnant, we actually do finally evolve into a turbulent cascade. So this is a lot more comfortable. As the supernova evolved, you can get to a region of cascade. We see our Kolmogorov cascade there.
How long does it take to go to the Kolmogorov?
So this red region here is about when so it's a set-off time. It's when the supernova, the reverse shock is propagated through the entire ejecta because it's swept up the same amount of mass that's in the ejecta. So it's very close to that set-off.
Sorry, I still don't fully understand.
Yep.
So in the previous simulation showing when it's self-similar, the profile, then you never go into
Right,
these
right.
cascade regime, right?
Correct.
So that means you constantly have the driving of the finger, so that
Mhm.
the morphology is like
yes.
the finger.
Yep.
Structure. So here, then it's different.
Right,
So
here we've
you're
added
saying
another
that-
scale to the problem, basically.
Okay, so then at that regime, you don't see the finger anymore.
Oh, you'll still see fingers, it's just they won't be, you know, they are undergoing a full turbulent cascade as well. So there will still be Rayleigh tailored fingers here, they're just going to be poofier. There will be some characteristic shift there.
And is there a because you are measuring angular power spectrum, which is the average over the radial direction, will that change the spectrum of this?
Not sure I understand your question.
I mean, I just wonder, so the cosmograph is a 3D power spectrum,
Yes.
right? So if like just in normal turbulence, if you average over one direction, as you did for the radial direction, we'll still get the 5/3.
I mean, we did,
Oh,
so. Right. So. Yes, and the other important thing to note here is that this L naught is shifting with time as well. Because your characteristic scale height of your density profile is now also time dependent, right, with this exponential. So it still traces that, we just have another scale in the problem. But we can break this scale for something like a real remnant, because for many of them, we know how old they are, we have historic data. We know when the supernova went off, this T is not just a computational T, there's a real T involved.
And statistically, what happens to the low L part? I mean, you have some peaks that grow, but always just realization.
Yes, so the strongest peak in his is because in 3D we did a quadrant. So again, it's still just a very steep drop off.
It's getting shallower than -3.
It is. But again, real supernovae will not be perfectly spherical, so we didn't do too much analysis with this yet. We did include the sloppiest way of looking at cooling. So we did do just a 4/3 power law, adiabatic index, to kind of simulate cooling. And I'm very interested to talk to some of you about how to do this better in the future. Very interestingly, when we include this cooling prescription, we never see this steep phase, L of -3, it immediately grows in Kolmogorov. There's almost a second steep power law over here, but it's questionable. But there is always a Kolmogorov cascade, we never get this, what we were calling the Rayleigh-Taylor growth rate over here. So this is something we can check out if we actually get to a point where we can compare this to real data. But again, this is the simplest cooling method. Hand wavy, just something does change. So, what about real data? Again, this was the old advisor saying, okay, well, there's a couple remnants with 3D reconstructions. I don't know that those 3D reconstructions are good enough for this type of analysis yet, but it'll happen someday, right? I'm patient, I have a whole career ahead of me. Show him again and say, no, I think we can do this now. I don't think we have to wait for all of it. This is Casse, by the way, all of our remnants to have, you know, full 3D reconstructions. That probably will never happen. Most of our remnant data, again, looks like this. This is Chandra X-ray images are kind of the big, shiny data sets that we have. So Sean sat down and said, I want to figure out a way that we can do this sort of analysis just on these images, right? And that's very hard because these images, they have projection effects, they have limb brightening. It's a hard problem to do. And again, in the past, there have been a couple attempts to do this. Laura Lopez has done a lot with wavelet deconstructions for just kind of the smaller angular mode, the larger angular mode, smaller L's. There's been a lot of work showing just even the first two L modes can distinguish between a 1A and the slightly less spherical core collapse supernovae. But the full power spectral analysis of an image, very hard. But Sean was very good. So he said, what if instead of doing the power spectral analysis, we do something called delta variance method, which is basically deconvolving things into a set of Gaussians and allowing you to add this M here, this mask. So you can mask out, you do many power spectrum over increasingly larger radii of shells in the image, right? And then you can, it's a way of deconvolving the projection effects because you're mostly comparing things along the same angle of projection to themselves. When he tried this the first time, it just totally was a mess. It was unfortunate. These different colors are different radii of different masks. And we get the same problem we get with Fourier transforms where you find out it's a circle. Remnants are circles. There's like kind of a bump here if we go to very small, shells in our system, but mostly we learn it's a circle. But he realized what you can do is subtract the do azimuthal angle subtraction of itself. And that kind of takes away that dominant limb brightening effect. And then you get the power spectrum again. So again, these are his simulations projected into a 2D image was the test of, can we do this on the models before we even touch data? So again, we do see something that looks more like the power spectra we're used to. There's a peak, there's a steep slope, and there's his quadrant, but there's this spherical behavior here, yes.
So when you're measuring the spherical harmonics from average over M, you can see whatever you're seeing is statistically isotropic, but in this case, it's probably not, right? Is this still baked into the
Right, so this is not now. Now we're no longer doing our radial average, we're just doing.
But it's not the radial average, right? It's
Right, so, right, you're right. So we are still assuming that they are fundamentally spherical enough that we can account for projection effects through the same radii, right? So and this should pop out anisotropies, but not projections is the hope. So again, this might not work for something like crab, but should work for something like a 1A remnant, and I think also a core collapse remnant. So he did it. This is our image of Tycho. And the other nice thing about the delta variance methods is you can add arbitrary masks. So we can also mask out these things. And we did so many tests to make sure we masked out these things properly. So I would just say, trust me that this is, your field of view difference in your chips. We accounted for that. I'm very confident we accounted for that. I was very not confident we accounted for that even like 3 months ago. But here's our broadband X-ray image of Tycho. And using the delta variance method, this is the power spectrum that Sean calculated. So we see a strong peak over here, potentially that dominant mode we're looking for here, we hope, and then a strong slope. And this is rough, right? I convinced myself it's there because I'm looking for it, but it's not necessarily horribly convincing until, right, here's the slope of L to -3. So this was very cool for us. This was also not rough. But when we take a look at the dominant angular mode and this kind of kink in the power spectrum, it does very nicely trace the thing I was talking about, these cauliflower leaves in Tycho. So I do think that this worked. I do think we're looking at the dominant mode here. And we can compare it because of this L naught and this slope. We can choose one of the time-dependent timestamps of our exponential ejector profile to compare it to. So that's here. This is our 3D hydro model. And again, we choose the time at which to the computational dynamic time based on matching this and the slope here. And again, these are the non-cooled ones because the cooled ones never have this steep of a slope. And from that, we can get some information out of this because we know the actual age of Tycho. We can use this to estimate things like the density of the CSM, which is, I think it's about factor of 2 off from most of the other estimates, so, you know, maybe that's error bars here, maybe it's a different way of measuring it, very early stages, but I think it's very cool. Obviously, an exponential density profile is not gonna be perfect either. And we can also use this to, again, get the density scale height of kind of the tangent of the exponential profile at the time, and we can start to compare these to remnant 1A models. And that work has yet to be done. This is the most recent paper using this methodology. But just we can do this on real remnants, and I think we should. And I think there's stuff to learn. But I think as we perform this on more remnants, we also need to perform this on more realistic explosion models. Definitely in the 1A case, but even more importantly in the core collapse supernovae. So I think I'm finishing a little early. I expected you guys to be a little bit more interruptive, but we can just talk then. But there's a lot to do in the 1A field. We have pretty good differing progenitor models. We should run those into the remnant phase. We should compare these to the dynamic ages of the dynamic evolution of Tycho and the other 1A remnants, and see if we can pull out anything about the progenitor of these type 1A supernovae from their dominant cauliflower modes. I'm very interested right now in the question of, well, we think 1As have companions, right? If we have a supernova run into that companion, there's always been this question in my mind of how can our remnants be so spherical, right? Can we maybe in this, maybe this over here, maybe this, I didn't talk about it, but there's this excess large power, which you can kind of see. We talked about it in the papers, maybe being running where it runs into a kind of lobe of dense CSM. It could be something, but it could also be related to a kind of weak from running into the ejecta, the supernova companion. But I've always been uncomfortable with the fact that I think you should be able to see that by eye, and we don't in any remnants. So I'm very interested in modeling this. Already I was interested in that, and I'm interested in looking at the imprint on the companion, or on the remnant rather. Core collapse supernovae, we haven't done any realistic models with this sort of analysis for yet, and I'm very interested in doing that. I do think, you know, when there's so many papers out there where we look at a remnant, we draw an arrow and say, this is a jet. We should be able to actually quantify the angular imprint of a jet on a remnant and highlight that and check, are these arrows we're drawing pointing towards jets actually jets? Again, nickel bullets, number of nickel bullets is very important. Distribution of nickel bullets is really important. It tells us a lot about the supernova physics. It's something we maybe can pull out of this data. And then surface asymmetries. And what I mean by this is, you know, you have a shockwave start inside the star. It's going to blow through these stellar envelopes. Those stellar envelopes should not be spherical. So this can be another sort of large scale, strong external clumping before it even gets to the CSM. Can we pull out those signatures? Shalom's moving on to his postdoc, and he's modeling pulsar wind nebulae is his main goal right now. He's very interested in crab-like objects and what we can learn about them. And it's a much harder problem for a lot of reasons. Like you said in the beginning, they're not very spherical. But he's interested in both the modeling side of those and then the analysis. Can we expand this to be useful in those regimes? And of course, we need to look at more remnants. We've only looked at Tycho in terms of real data. And last I put up there, what the heck is PA30, which maybe since I have a little time, I'll go into for a second. So since I started paying attention to remnants, I started reading the remnant papers. And this weird remnant was just discovered, PA30. This is one of NASA's images of the day. It's a Milky Way remnant recently discovered and associated with a historic supernova, 1181. The supernova went off in 1181. It was observed by scientists in China and Japan. And they believe that this is the remnant of this. And it is the weirdest remnant I have ever seen. It is wildly spherical. It has these strong filamentary structures, and it has a surviving central object. If we look at it in sulfur, it even appears like wildly more spherical. But these filaments are these intermediate mass elements, they're sulfur, argon. And we have no idea what it is. It's been pointed to as maybe a 1AX. And this central object is the surviving merger of two white dwarfs. And I asked the question, one, how do you make something with this structure? You can't do this with turbulence. I don't like it. And if this is a merger process, if this is the weirdest, most asymmetric type of type 1A supernova, why is it the most spherical remnant? So I'm thinking about this a lot now, and I care a lot about this, and I wanted to bring it up in case anybody else here cares a lot about this and would like to talk about it. What?
It's the character of the central object.
It is really hot. It's about 200,000 Kelvin. It's rapidly rotating. They think there should be a very, very strong, like 16,000 kilometer per second wind was reported. And again, that makes this harder. How do you make something spherical with that strong of a wind? It must not be losing that much mass, or I don't understand winds. But yeah, it's wild. There are a couple spectra of it that show very, very broad calcium and oxygen. But yeah,
Between the size of the central object, the size of.
compact. It's an unknown compact object.
You have a temperature, you have a luminosity.
With a scale.
Yes, yeah. I don't remember what the scale is off the top of my head, but it is on the verge of smallest neutron star, largest white dwarf. Right?
No, the other way around.
The other way around, yes.
Largest
Largest white dwarf, smallest neutron star.
Yeah,
No.
well, I mean, there's still many orders of magnitude.
Yes, yeah. But there has been no strong statement of what the central object is other than weird.
It wasn't observed in X-rays.
There is one, it shows up in X-ray. There's XMM Newton object. It shows up, but it's not a high resolution. It's kind of,
When was it discovered, this object?
these filamentary structures was 2020 to 2023. There is infrared data that is older than that, which is what you saw in the composite.
How distant it is? I mean, what is a
It's-
scale of arc seconds or, well, arc minutes probably?
I think it's small. I think the total diameter is about
170 according to Wikipedia.
107, well, that's the,
Arc
Light
second.
years or?
No, sorry,
that's-
arc second.
yes, yeah, so I think it was like, yeah.
And a distance?
I'm gonna
It
mess
says
it up.
from Gaia, it says it's 2.3 kilo/second.
Okay, yeah, it's very nearby.
So where did we get
No,
the
2.3 kilo.
Where do we get the temperature from? The spectrum. They just have one optical spectrum and they did a black body fit with it.
Yeah, I mean,
You're in the
ultraviolet data.
It's like a listen.
No, yeah, that's his,
Ultraviolet data,
I-
really Gene's tail.
yes, I agree. I agree with your raised eyebrows. I agree with your raised eyebrows. I think there's a lot to do with this. And I think the things we know have giant error bars. The wind and the central object was just one Nature paper. And we need more data. I have tried to leverage my last semester of Keck time through Caltech to image this better, but do some IFU imaging, so we'll see if they bite. Yeah, yes.
So,
Mhm.
I guess the stars are just background stars, right? They're.
Yes, except for the central object is this guy.
Okay, okay.
But yes, most of the stars are foreground or background stars. And this is our central. It's very weird. It's incredibly weird. It's incredibly uncomfortable. Yeah, we had one idea. I don't know, we just posted, which was in our group, which is you can, with really strong cooling, really strong line cooling, suppress kind of the Kelvin-Helmholtz turnover of Rayleigh-Taylor instability and get something. And this is the only theoretical model I've seen that's been able to make this spiky structure, but that doesn't mean it's necessarily right. But it's a puzzle, and it's a puzzle I like.
So, Going back to the method, we try to measure our spectrum of remnant. Yeah, so this one, I wonder, do you have an explanation of why it's, it seems very different in the low L, right? The power. When you compare it to simulations.
Right, well, that's a good thing. It's a good thing, right? Our simulations are perfectly spherical. The real world is not.
Oh,
So this peak here kind of traces out a circle along here. There is this bright edge, and we think that's what it's picking up. But I think there's a lot of science we can ask about the fact that it is different here.
yeah, like the peak at
Yeah.
around 1 or 2,
Yeah.
3.
Yeah.
That's. What is that? Is that just the size of this disk?
No, it's not. It's about this large if I draw it on here.
Yeah,
Yeah.
but by eye, we don't see such a structure, right?
There's an ear here. There is this, again, what we think it is there's this arc of extra bright material here. Which again, that could be an asymmetry in the supernova. It could be an asymmetry in the CSM.
Well, one of the questions is that if that's the structure you're seeing, why is it a peak? Such a high peak relative to the other
Yeah.
structures?
I agree. And this is why,
Visually, I don't see a peak.
I know,
I mean, it's such a strong peak.
yes, I agree.
I can't
And
do
that's
further
why I think
analysis
it's
with my eyes.
this is cut off here. Let me see if I can bring up the actual image of Tycho. I had it. It looks better in.
Or
mine.
is that just a reflection of the artifact?
So,
No.
if we look over
Okay.
here, I don't know why this cuts it off in the screen. But there is an ear here that is around that angular scale. Let me see if I can bring up my Tycho image. Yes. So this guy, it's about this scale. So I think it's picking up this personally. But
So that's some signal only coming from the largest ring.
Yes.
When you measure.
yes, yeah. So low L is big angular modes. So
Yeah,
that's
but I
about
guess
right.
you're measuring the power spectrum ring by ring, right? To
Right.
project.
yes. So that big one is only coming from the outer edges.
Yeah, so
So
it
again, it
seems
could be
like
this, or it could be this region here is also very bright. We're working on it. Yes.
Why don't you use this figure instead of the other one? This seems to be
this is-
to have clearer structure than the other one.
Yes, well, this is partially artificial, right? So it's artificial coloring based on other things. It turns out X-ray data is very hard to make decisions about. Right, and different decisions you make can make it look better or worse by eye, but may not translate to scientific accuracy.
But you can actually do this analysis for different wavelengths, for different elements.
Yes, and we should do that. We did not yet because our models were constant composition, but that is one of the things I'm very interested in doing with something like my actual explosion models obviously have compositions, right?
Comment and a real question.
Yes,
The comment is on the Rayleigh-Taylor
Yeah.
power spectrum. In the images of your simulation that you showed,
Mhm.
that was classic Rayleigh-Taylor
Yes.
shapes.
yes.
So I don't see why you even expected isotropic Kolmogorov turbulence.
Well, yeah, there, yes. In the self-similar, we did. In,
Yeah.
you know, something that actually evolves, it's,
Yeah, and it's an ancient literature on this.
yes,
And classic stories that for linear modes, the short wavelengths grow fastest.
Yeah.
In the nonlinear regime, it's the longest modes up to the dimension of the box.
Yeah.
And eventually what happened to your situation is all of these things start hitting each other. And then once you're looking at a small scale with screens coming in from different directions,
Mhm.
then it's looking more like isotropic turbulence.
Yes, it's not as surprising as I make the story out to be, but it's still uncomfortable when you try to do something that measures the growth rate of turbulence and you never see it, right?
And it may be also worth remarking that in that classic literature, the perturbations are taken as incompressible.
Yes,
So that's a very stiff equation of state.
yes. Yes, whereas is compressible astro, so yeah.
The real comment is in your analysis, you came up with that what characteristic L.
Mhm.
Your cauliflower florets, so to speak.
Yep.
And yes, you can see them in the image.
Mhm.
And it also would be interesting to ask, are they the same scale in the different atomic features?
Right.
But you promised us a physical mechanism for them.
Well, I told you the density scale height.
So even in here, I want to explain that the density scale height was sort of artificial prescription. So this is now a density scale height in the eject.
Yes. Yes, it continued to trace our density scale height, which is now a function of time in more realistic simulations, right? So it traces that across time. Yeah.
All the more reason to see if it changes with
Yes,
different
with different
abundances.
abundances and in different remnants, right? There's always this big question between Tycho and 1006, right? That they seem to have disagreeing dominant modes over time, right? One is older and it should have wider modes, but it has narrower instead. So. Yes.
So the observation agree more with a self-similar model because it doesn't show homomorph. This is how we should interpret it.
Sorry, one more time.
The observation doesn't show homomorph, doesn't mean.
Oh, no, the observation doesn't show Kamal graph, and I interpret that as Tycho is a young remnant, dynamically young.
It doesn't have enough time to develop.
Yes, exactly.
And the last in this very strange object that I showed, is this possible that expansion is too fast and there's no time for the instability to develop?
Technically, yes, but then what are the narrow features? Right, something else has to create them then. Right, then you'd have to have a structure of your supernova that contain those, and that's not what supernova explosion models look like, especially thermonuclear supernova explosion models.
And we know the age of it, right? It's something like. what
We do know the
Purdue
age,
does.
but young versus old for remnants gets tricky because it's not just the age, it's how dense is the stuff around it, right? So it's a dynamic age.
So do we have more questions?
It would be nice to see this in velocity space, so that
Yes.
you line profiles. and-
Yes, we have all of that in the papers too. And that was one of my original hopes was there are a lot of good papers that come out with velocity reconstructions of remnants and but it turns out they're still very messy. They're messier than I hoped they were. But yes, all the velocity profiles are in the paper as well. We just stuck with density because it was easier to
Talk about
predict.
the decomposition.
Yeah.
And the L decomposition in velocity space.
Yes, we did that.
So there are IFU observations so that you can.
There are not,
measure
we
the
hope
length.
there will be.
Oh.
That is what we asked for and we'll see if the TAC approves it.
How many supernovae like this are there to study?
Roughly a dozen.
Dozen, even though there are about 300 in the galaxy.
They
They're all
have to be,
closed.
they have to be nearby and they have to be well imaged, right? So.
Yeah, Roman.
Presume you're not doing MHD in these cases. But then, it's not, I don't expect magnetic fields to be dynamically.
Right.
But what can happen is that, these Rayleigh Taylor fingers, they have very specific
Right.
shapes, and they can, any field that will be dragged in there can be
Yes.
stretched along, and then this will give signatures in a polarization of radio emission
Yes.
from this remnant. So I'm wondering if this is something, that should be attempted, just in a kinematic limit,
Yes.
see the magnetic field, see what structure you get, and calculate the synchrotron emission and compare these observations. Because I think people do this polarized observations of remnant.
Yes, they do. And that, I'm very interested in the hard new physics that I'm interested in doing is very much that and real cooling prescriptions for your synchrotron cooling. Because if we, with our just our weird gamma law, it's doesn't change the fact that, you know, in real life, your forward shock is pulling, but your reverse shock probably isn't. So it's, there are going to be real differences, and those are, I think, big physics we're missing, but I'm of a philosophy of always start with the simplest and see, you know, what more physics then adds to the understanding.
The more I stare at your crab image, the more it looks like PA30.
A little bit, kind of, but it doesn't though. I mean, it's got veins and it's got holes punched into it, and this is what a wind does, right? It punches holes into the ejecta. It doesn't create, you know,
Yeah, these are
goofball filament.
they're not straight line rate.
Yeah, the only thing that I found that looks like those are in planetary nebulae, right? In something like the Ring Nebula, there's that region of those narrow figures. Yeah. Yeah. But they're wildly different temperature and composition in the planetary nebulae.
It's just illuminating vectors. You'd expect it to, with cooling, that there would be a density correlate with that, and so they have that density as
Some severe little.
I don't think they do, but it does trace strong cooling lines of the intermediate mass elements. So again, oxygen, argon, sulfur.
They would be.
But yeah, there's more to do. I'm very interested in the question of, is it cooler or hotter than the gaps, right, than the forward shock? So I think there's just so much to learn, but it's hard. We've been fairly unsuccessful in proposing time for this because we have to pinpoint what we'll learn by looking at it. And yeah, it's I agree.
It's not allowed anymore.
Yeah, but that's the feedback of we want to know exactly what you're testing to learn. And so that's why I've started trying to model things and distinguish between sources and that kind of thing, because it is an easier case to make if we say, okay, well, here's what we will actually learn from this observation, instead of, oh my God, it's just one WST pass, just look at it, please. So.
I think we are passing 12. So let's thank Abby again.